Hello, this is John Black, Superchemist. This is part 5. So we already did the math. There's no more math to do. But I did want to, we didn't really talk about what these actually represent. We just did a generic definition and did the math, right? But before we get into that, I want to talk about this here because it's just one minute thing here. This is a unit circle. There's your X and your Y and then your diagonal, right? And what's going on here, right? This is defined as two rays coming from the origin here, right? We got one ray that goes up to here to the circumference, and it goes around the circumference, right? Then you have another one that goes along the x-axis. It's stuck on the x-axis. It's fixed, right? Fixed to the x-axis. The only one that moves actually is this one, out of the x-axis. So you need to, because I think a lot of people are confused with this lie, right? That cosine equals x and y equals sine theta. This cosine theta and sine theta, they do not equal y and x, okay? That's a lie. They only equal that on a unit circle, okay? That's why they need to stop shortening the equations. All it does is confuse people, okay? Cosine theta is adjacent over hypotenuse, okay? Not x, all right? Adjacent would be the x, you know what I mean? Or you can say cosine is adjacent over radius, okay? Because the hypotenuse, right, is the radius. Either way, it doesn't matter. That's the, it's not cosine theta equals x or adjacent, okay, to this theta. No. They just shortened that. That's only for a unit-shaped circle. It's the same way with the sine theta. See, on a unit circle, okay, the radius, right, or the hypotenuse is always 1, right? And you can see from these formulas here, hypotenuse or radius, is always at the bottom. And if it's 1, then you can just take, anything over 1 as itself. So you really don't need to put the 1 in there for cosine theta and sine theta. But you should, the teacher should the kids put them in it. Put the thing there. I don't care if it's a 1 or not, because you're confusing people. And the reason why I'm bringing this up is because look on our example. Cosine theta is in the y-axis, and sine theta is in the x-axis. That seems wrong, but it is actually correct, okay? Because when it comes to the unit circle, we assign. As a matter of fact, in here too, we always assign what x is, okay, or what cosine theta is, okay. So what is the real way to know what is cosine theta, right? Three things down here. See here? One is the theta thing, the theta angle, right? You're going to have that theta angle touching cosine theta. So it's either one of these two lines here, right? The second thing is it has to have a right angle, right? It needs to have that angle, right, where that angle is. It needs to have a line that goes all the way up to hit the circle, right, the circumference. And that intersects, it will intersect where the hypotenuse or radius is. And the last thing, the third thing is that it's fixed. You know what I mean? In that axis. You know what I mean? Like the x-axis, you can't. This guy here, the cosine theta, he cannot move off of there when it's a unit circle, right? So those are the three things. Because look at the sine. Yes, it has a right triangle, like over here, right angle, but it doesn't have the theta. And the hypotenuse, right? Yeah, sure, it has a theta, but it doesn't have a right triangle. Only the cosine theta has a right triangle and a theta, right? And when you do all this over here, you never really care about the sine, right? So you only have two lines, right? So you know where the theta is because you only have two lines. If you only have two lines, you only have one angle. That means you know where theta is. But you see, this is a unit circle. We assigned it. We could have just as well assigned it to the y-axis, right? We could have just said it was the y-axis, but we didn't. So let's go to our problem here, right? This is actually one problem, right? I just am doing it two different ways, right? This is the proper way. This is the way I do it right now, but it's not actually proper. And you shouldn't do it this way because sooner or later you're going to get problems where you have things like this and cosine theta is not on the x-axis, x-axis relative to the Earth. It is on the analyzer in this situation here, right? And then you get all confused. What some people do is they just reorient the problem, right? The problem was the analyzer is vertical. This is coming in at, say, 60 degrees, right? So theta is 60 degrees. I have it up here. Now to do the math, you don't need to know all this stuff, right? You just plug it into this over here. You got your theta, get the cosine, and blah, 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 right? But we're not doing the math now. We want to see what these lines are and what they, because it took me a while to figure it out, right? No one tells you what they are, all right? So before we get into this, right, let's talk about these two thingies here, right? We'll go real quick, right? Here you got the north and south, two big giant magnets, and you have a detector in between. Let's just call it a piece of paper, right? You can see you have horizontal lines going this way. That's the north flux lines going from north to south. Then you have this black line here that's horizontal, right? It's parallel with the flux lines, right? That line is also like the normal or perpendicular to this piece of paper, this detector, right? It's coming straight out of it, right? So they turn the magnet on and they count up these lines that go through this detector, and you get your how many lines. More lines, you got more power, more force. You know what I mean? But let's say you took your paper and you tilted it, right? And say you had the way they're having it, they have it like this, and the thing goes like this, and it goes like that, right? What if you tilted this down like that? Now it's kind of like deflecting. Half of it seems like it would be deflected off, right? You know what I mean? You wouldn't get as much power from each one of those flux lines, right? So now, okay, you have a normal here. Your normal is still here. Here it's black, here it's red, right? Look at the normal now. It's still perpendicular to the plane of the paper, right, the detector, but now it's at an angle. It's at 45 or 60 degree angle, right? Now look how it makes two lines, right? The one line is the normal for the paper or detector, and then this line right here that's black used to be red. It's these flux lines, right? That's in the X, and it is static. So you're not going to get as much, force from these flux lines, you know what I mean, if you have an angle here, okay? This is your theta, right? Now look at this one. There's a box. You want to move the box from left to right. The best way would be to move it horizontally, give the force right here. But you can see the red line, right? Again, it's at an angle, right? And again, you get a theta in between these, and you have a horizontal x-axis line here. This is where you would want to do it, right? You'd want to push it from this, and say, because half of your force this way is going down, and that's going to make the box go down. But if it's on the ground, that means it's not going to do anything. It's not useful at all. Okay, cosine theta is x on this magnetic thing here, right? But notice how that the flux lines are static. They don't move. The magnets are big. They're just sitting there, right? They move the paper, right, or the collector, or the detector, or whatever, right? But they never move the flux lines, right? Same with the box down here, right? It's what we said the x-axis was the cosine theta. It never changes because it's due to gravity, right? These forces that are in the x-axis, they don't change. They're same way with this, the analyzer. It doesn't change its position, right? You were the one. The photon is the one that moves. This guy right here, he moved the paper. You moved the box. You know what I mean? Those are not static. So that must be the hypotenuse, because you only have two choices, right? So this one right here, I rotated. Okay, you can see the analyzer was here. I just basically rotated it down to here. And then this axis, right, this red part, it should be here. But I just put it up here because I want it to be in the positive axis, okay? It doesn't really matter. When you're just doing this, the only thing that matters is the degrees. 60 degrees apart. That's it. Yeah, that's no matter where it's at on this thing, right? But like I said, later on, when you have more complex problems, you're going to get You're going to get mistakes with this. So we already have our two lines here, right? Which one is the cosine theta? Normally, you would say, oh, it's the horizontal one would be cosine, right? But there is no horizontal lines here, is there? There's a vertical one and there's this diagonal one. So what do you do? All right, and this confused me at first. All right, but this isn't the way. What I'm going to say right now, it's not really scientific. It's just I'm telling you my thinking process of how I figured this out. Okay, all right. The red one here, right? The angles on both of these examples, right? What are they? They're the hypotenuse. Do you know how I know? This red line, that is the origin of your, force, right? That's the reality, right? This is what happens. This is the first thing. It's the before. You got a before and you have an after. Before is the hypotenuse. The after is the cosine. Sometimes it's on the x-axis, but sometimes it's not. Only on a unit circle was it always on the x-axis, okay? So how do you determine the difference? You have a theta here. It's touching both lines. What can determine what's what? Like I said, this is you in this example, right? You're a photon diagonally, and this is me over here. I'm a photon too. I'm diagonal, right? We're going into the polarizer, right? This is the original. This is reality. See, reality. Reality is I am this, or you are that, and I'm this, right? We are photons, and this is what we are, okay? What do we want to be? What would be better, okay? Right here. What would be better? It'd be better to be in this x-axis, wouldn't it? Staying up here. It'd be better to be in this x-axis, right? What about up here? What would be better? The best would obviously be right here, going in vertical. So that means that is cosine theta, which some people might say is the x-axis. You can call it the x-axis, but if you do that, that means that, like I did this over here. I rotated it around, okay? But this means that the ground on planet Earth is vertical. See how I'm doing this? Okay, over here on planet Earth, the x-axis is horizontal, okay? It's all just a relativity thing, you know what I mean? You can turn it over like this and have this be ground, but it's the same thing. They're the same exact thing, right? So the cosine theta, okay, it's not always the x-axis, but it's always the destination or what you want or what happens after. You know what I mean? It's a better situation, and the hypotenuse is always the origin, the first, the reality. You know what I mean? It's the reality of what and this is before and this is after. Okay, always. Okay, you have to describe them in some type of thing like this, right? Because they all want to be in this axis, right? These, they all want to be in this axis. These right here, they all started out in the red. They all started in an angle, okay? So that's how you figure out which is the cosine theta and which is the hypotenuse, okay? Now I want to remind you, these two formulas here where they use cosine theta, they're not squaring it, okay? Like for this force one with the box, I wrote it down right here. You can see it's force cosine times theta, right? It's not squared, okay? So that's important to know because when you have sine, we're going to get into sine here soon. When you square it, like we do up here, right? That means that the sine, the squared, when you get this over here, right, is the percentage of the stuff that was bad. And in this case, good and bad is whether you went through the filter or not, okay? The percentage of light that didn't get through. The cosine up here, right, when you plug it into here, right, since you're squaring it, tells you the percentage of the photons that do make it through. See, when you do these formulas, when you don't square the cosine theta, you find out the percentage, again, of this good stuff, right? You know what I mean? The force that helped you here, but the sine, okay, it does not tell you, it's not a percentage of the stuff that didn't go through. It's not, okay? Only when you square it, like over here, okay? So keep that in mind too if you do these kind of things over here. The sine is nothing. It doesn't really tell you much. The analyzer is static, right? It doesn't move.